do. Thank you, John O. Welcome to our May CONA meeting to everybody. We'll get started in just a minute or two. Do we have any elected officials here or candidates for office here tonight? Well, they're not worried about sea level rise, I guess.
This is the night before the election. Give them a break.
Never give a candidate an even break. Come on. Well, tonight our program is going to be on sea level rise and implications and all sorts of stuff. And Laurie Muldowney is going to be in charge of this program. Laurie's specialty has been historic preservation. She's spoken here before CONA before. There she is. And she will be introducing all of our speakers and telling you more about the program, but we do have Tim Rummage, David Schaefer, and Jack Merriam here tonight to participate on this subject, which is certainly important to many of us. Some of us may not be around by the time it gets to be really difficult, but my family has a beach house on Anna Maria that's been there since 1912, and I hope at least it's going to outlast me. My kids, well, they can worry about it and figure out what to do or how far they have to jack it up over the next few years. But this program tonight will be taped, and we will put the tape as soon as we can manage to do it out onto the CONA website, conasarasota.org. All of our programs are videoed, thanks to volunteers who do that for us. Tonight, Tom Matrullo is doing it, so that if you want to go look at it again or refresh your memory or refer to it to a friend, that's what you do, conasarasota.org. Afterwards, later we will have a question and answer period, and I would ask you all to wait to ask your question until somebody can bring a microphone to you, because if we don't use the microphones, it will not make it onto the recording for the video. And there's nothing more annoying than to watch a video where you don't have a clue what the question was and therefore don't understand the answer. So please, when you want to ask a question, wait for somebody to get a microphone to you. Do we have anyone who wishes to make an announcement before we get started about what your homeowner association or concern that you have that you'd like to mention? If not, Wade, did you? Wade.
I'm unfortunately, the president at the moment of Better Government Association, because in case some of you don't know, Aisha Summerson, who is our excellent president and a staunch relayer of economic expertise, and she was a great expert, passed away about 2 weeks ago, 2.5 weeks ago. And so I'm trying to fill in then for her. And we are having a forum on, of all things, something similar to this time, and only we're not calling it climate change, we're calling it sea level rising. But we're also going to try to focus on Sarasota, and it's going to be this coming Saturday, May 13th, 2 to 4 p.m. down at the Gulf Gate Library. In case you want to know a little more, Tim Rumage is going to be one of our speakers right here, and the other one will be Stevie Freeman-Monty, Sustainability Manager for the City of Sarasota. So if you'd like to learn more about this, see you on Saturday. Thank you.
Thank you, Wade. So we have two opportunities coming right in a row to immerse yourself, so to speak, in this sort of thing. So without any further ado, I guess, Laurie, would you like to come up then and take over and get the show on the road, as we call it?
Thank you, Bill. Well, it's wonderful to be here tonight, and we have a nice audience and a lot of people interested in a topic that I've been learning a good bit myself over the last couple of months. My background is historic preservation, and I've talked to CONA in the past about historic preservation and building codes, but really what is a hot topic now among historic preservationists is how are we going to deal with climate change and sea level rise. As you might expect, many historic properties are very vulnerable to these threats. They were built long before building codes required setbacks from the coastline, and long before buildings had to be fortified against extreme weather conditions. So it's a big topic of discussion for historic preservationists. So we have some fine speakers here with us this evening. I'm going to introduce all of them now, and then each will talk for a period of time, and then at the end we'll have plenty of time for questions and answers. So the first one of our speakers will be Tim Rummage, who is the co-founder of This Spaceship Earth and co-author of the recent book bearing the same title. Tim is also the coordinator and professor of environmental studies at Ringling College of Art and Design. Second, we will have Jack Merriam speaking. He's a natural scientist with extensive governmental experience in water management and is currently a director on the boards of the Sarasota Bay Foundation and the Suncoast Waterkeeper. And concluding, rounding out our panel and speaking at the end will be David Schaefer, who is the executive director of the Science and Environment Council. He will discuss the recently launched Sarasota Manatee Climate Council, which is an independent regional work group that aims to advance understanding of climate change. So with that, I'll go ahead and let Tim get started. Thank you.
Thank you very much. I want to sort of do the broad planetary view of what's going on with climate change, and then Jack's going to turn it over and do more of the local impacts. So the environment can be humanity's greatest friend, or if poorly managed, our most implacable foe. And certainly for Sarasota's history, we certainly have enjoyed the greatest friendship part of this arrangement. But as we start talking about climate change, there's a whole variety of things that are at risk from environmental point of view and an economic point of view. What we're talking about here is the fact that, as said, climate is an angry beast, and basically we are poking it with sticks. And so if you want to know whether or not global warming is happening, the answer to that is yes. I'm just going to play this clip. It runs from about 1950, pretty close to the present. And you're going to be able to see as we approach this color band in here, it just means that we're hot. So yeah, we're hot. We've been warming the planet for a while now. And the real reason for the warming is the increasing levels of greenhouse gases in the environment. And then these things then trigger things like global warming, climate change, sea level rise, extreme weather events. And the primary greenhouse gases we're talking about are carbon dioxide, methane, nitrous oxide, and fluorinated carbons. The question that I get from time to time is this really human caused? Are people really the source of this problem? And the answer to that is yes. If we start looking at what we're seeing, we know that fluorinated gases, which have the potential to cause a great deal of warming, are human because we're the only thing that makes them. Nature doesn't make that type of gas at all. The numbers in white here are the magnifiers. Relative to carbon dioxide, how much more heat do any of these other chemical compounds cause? So with fluorinated gases, they are anywhere from 6,500 times as heat trapping as carbon to 23,900 times as heat trapping as carbon dioxide. Translation. Sulfur hexafluorine, which is this one, the worst. 1 pound of it can trap as much heat as 11.5 tons of carbon dioxide. Okay? Methane is about 21 times the heat trapping capability of carbon dioxide. Nitrous oxide is about 310. And so as we start looking at alternatives to issues with carbon dioxide, keep in mind that we really don't want to start depending more on these gases. You know, natural gas does not release as much CO2. That makes it sound good. Natural gas basically is methane. The numbers say, no, it's not really the way you want to go. So part of the problem we've been having as humans is the fact that there's a real difference between the way we sort of see how the world works or want it to work and the way it actually does. And so we're trying to get those things back in harmony with each other. The other way that we know that humans are the cause of this is if we look at the different isotopes of carbon, carbon-12, carbon-13, carbon-14. Carbon-14, this is the one that's used in radioactive dating. Carbon-12, carbon-13 are the ones we really look at in terms of human impact of climate change. Biological systems prefer carbon-12. Atmosphere plays carbon-12, carbon-13 the same. So all fossil fuels were biological in origin. There used to be algae and plankton and animals and stuff like that. So those carbon fuels have a higher percentage of carbon-12 in them than you would find in the normal atmosphere. And as we burn that fuel, what we see is an increase in carbon-12 because we're burning basically biological material. And so the release that's taking place and this increase in carbon dioxide from just looking at its makeup says it's from sequestered carbon. It's from the stuff that used to be in the ground that we're now putting into the atmosphere. So the global trend for temperatures, looking at the different scenarios, while the ideal goal is to try to keep us somewhere around 1.5 at the most 2 degrees Celsius, if you look at the climate agreement that was arranged in Paris, if everybody did exactly what they said they were going to do, we're still going to be about 6 degrees Fahrenheit warmer. And if we don't do anything, we're going to be about 7.6 degrees Fahrenheit warmer than we are now. And that is hugely problematic in terms of melting ice and sea level rise. So to give you some idea of how much carbon dioxide we're putting in the air, as of this afternoon at 1 o'clock, humanity had put in a little over 13 billion tons of carbon dioxide into the atmosphere this year. Okay. Now to translate that, my favorite way of doing it is elephants. Okay. Average elephant weighs about 4 tons. So to get 13 billion tons of carbon dioxide into the air so far this year, that is the equivalent of launching 300 elephants into the air every second of every day. Okay. And I think if you saw that happening, you would ask some questions. You would have some real questions about whether or not that was a good idea. Okay. And when you saw those elephants hanging over your head for decades to millennium, you would really ask some questions as to whether or not putting all that carbon dioxide in the air is a really good idea. But because this stuff is invisible and odorless and tasteless, it goes past us. It's out of our frame of reference. And so we don't have that necessary conversation. Okay? Now the trend over the last several years has been just a continuous increase in the amount of carbon dioxide in the atmosphere. Right now, at the end of April, the average for April was 409 parts per million of carbon dioxide in the atmosphere. We have now peaked over 410 parts per million. But this chart, this animation, is sort of going to put this in perspective. What you're first going to see is what we've done in the last 60 years. And then we're going to run this whole thing back about 800,000 years so you can see the changes over time. So the up and down, this is the Mauna Loa, this is the Hawaii graph. The narrower range graph is from a station in Antarctica. So this stopped in 2014, so remember we're now up here. And now we're going to run this back to the, through the industrial, to the start of the industrial age. So pre-industrial level of carbon dioxide was averaged about 278 parts per million. And if you want to run it all the way back, looking at glacial cycles and natural warming cycles on the planet, run back about 800,000 years. You know, the average was about 185 parts per million. Okay? And humans come into this equation right in this level, right in here. Okay? So the number where we are now is way off what historically the planet has gone through. And so we have basically broken this natural cycle of heating and cooling that the planet has had for thousands of years. Now, some people ask me, when they see how high that dot is, they go, well, if the dot is running up so fast, why isn't the temperature running up at the same speed? And the issue is that what we're really talking about is the trapping of heat. Not necessarily temperature, but of heat. Okay? And heat is a form of energy, and it can be moved and interact in lots of different ways. Because most of the planet's surface is ocean, what we found is that about 90% of all the heat that's been trapped has now ended up in the ocean. And about 35% of that heat has managed to work its way down about half a mile into the ocean. So we've warmed the first half a mile of the ocean while we're doing this. Yes, we've also warmed the air. The other thing that we have done is we have used that heat to convert solid ice into water. We've used that heat to do thermal expansion of water. And we've used that heat to influence and impact the size and frequency of extreme weather events. Okay. So sea level rises for basically two reasons. One is thermal expansion. As water gets above 40 degrees Celsius, it expands. And the other is the calving and melting of land ice. Okay. If I melt sea ice, I don't raise the water level until that gets warm, and then it starts to expand, and then I'll raise it a little bit. It's the ice that isn't in the water that's now sliding into the water that is actually one of the major causes of sea level rise. Okay? And then as it melts and expands, it amplifies the situation. So the Earth is warming, but one of the things to point out is that the poles, the Arctic especially, is melting at twice the global average. So this is why we're starting to see the ice melt at the North Pole, and as you'll see in a few minutes, we're also now starting to see it melt much faster in Antarctica. So if you were to melt all the ice on Greenland, you raise sea level about 24 feet. You melt it all in Antarctica, you raise the water about 186 feet. Okay? I just want you to know that there's lots of ice. Okay? And it wants to do something. So, okay. So sea level change isn't new. As you've seen with the ice, normal ice age cycles, it rose and shrank, and it rose and shrank. Now we're in a sort of a different theme. It is the first time that we've ever witnessed anything like this, and it's actually being caused by us, not sort of the natural, historically natural geological or solar processes. So we basically are both the cause and the potential solution. So this is Florida when it was much wider, about 20,000 years ago. This is what what Florida might look like if you were able to raise sea level by about 5 meters. Okay. Now, one of the things that happens is the scientists get together and they make the projections as to what's likely to be happening with sea level rise in the future. And the tendency with the models is to make these really, clean, smooth curves. Okay. The reality is, ice melts in pulses. Historically, that's what it does. A lot of melt for a while, and you get very little, then you get a lot of ice melt, and then very little. So you can see, gradual ice melt, rapid ice melt, gradual, rapid, okay? So it's not going to follow that nice smooth curve, okay? Even in the 20th century, it's been a very bouncy system. But the main thing to notice is that overall, on planetary average, it's rising about 1.9 millimeters per year. 20th century, now it's rising about 3.4 millimeters per year. So the rate of change is going up. There's also going to be some confusion as we start talking about sea level rise in the future, as the numbers are going to be different. And part of this is not that sea level will have been dramatically higher in one place and lower someplace else. There are other issues that are at play here. One of them is subsidence. Okay? Off of New Orleans, sea level rise, people recorded as 46 inches of sea level rise. Actually, it's only been about 8 inches sea level rise, and a little over 3 feet of New Orleans just sinking down into the muck and mire. Okay, California, around Los Angeles, its landmass has been getting higher as the plate tectonics slide underneath and push the upper level of land up. Okay, so you're going to see some different numbers in different parts of the world as this goes on, and trying to keep it straight as to what's sea level rise and what's another geological process that's sort of important to be aware of. Okay? So, as Poe says, prevent the enemy is us, and so we've got to figure out, sort of what we're going to do. Now, part of what happens with the increasing levels of greenhouse gases, besides causing global warming, climate change, sea level rise, extreme weather events, is that these things all interact with each other and multiply their impact. Okay? So they have impacts of their own, and then they add to each other. So the changes are going to be, everything is going to change. It's going to change everywhere. It's going to change simultaneously. It's going to change synergistically. Okay? And the other thing that will happen is there's going to be a change in the rate of change, and the rate of change is going to change. So the rate of change may speed up, but its rate of speed up will also change. Okay? And part of the big question in here about sea level rise is we don't know, we don't have a good way to tell how fast ice will melt. That's really the wild card in here. Okay? But basically, what I always keep in mind is that what has happened in the past is not really a successful model for what's going to be happening in the future. Okay? So we're going to see changes in temperature, weather, coastlines, rivers, land formation, water supplies, ocean currents, toxicity of bacteria, acidity of the oceans, vegetation patterns. Everything's going to be changing. Okay? One of the things that happens with climate change is there's an increase in wildfires. Okay? On the western states, since the 80s, wildfires are now 4 times as often. They're about burning 6 times the land value of land area, and they're lasting about 5 times as long. Florida right now has 120 wildfires that the state is fighting at the moment. Okay? As sea level rise increases, there's going to be push on our freshwater supply as you get lateral intrusion as the salt water just moves in. And to a certain extent, that can be modified and amplified by how much water we're pumping out of the ground, which will actually suck more seawater into the system. Okay? We know that oceans are warming up, and right now they're warming about 4 times faster than they did in 1990. Okay? So global temperature scans back in the 50s are relative to the 2000s. Okay? And part of this then triggers things like the coral reef die-offs and the where the coral is expelling the algae that it's symbiotic with. And then if the water doesn't cool enough soon enough, then there are other types of algae that come in, filamentous algae that come in and basically cover over the corals, making it almost impossible for the symbiont algae to get back into the corals itself. We've also started to see changes in water currents, that as we melt ice up here and increase the amount of fresh water, therefore, that's in the Arctic Ocean that's coming down, that changes the salinity, it changes the temperature, and we're seeing it push on the Gulf Stream, so the Gulf Stream is not flowing as fast in the northern part of its current as it used to do, okay? We're also, with the increase in carbon dioxide, starting to see an increase in acidification of the ocean, where we're starting to see some impacts on shellfish and other marine life. But let's go back to sea level rise. Looking at the Arctic, and it's 3 degrees Celsius warming so far, and give you some idea how sort of fast estimates have changed. In 2013, the maximum estimate around for the year 2100 was, about, 3.3 feet. Okay. By 2014, the estimate was that we were going to get 11 inches of increase in water sea level rise simply by thermal expansion, and plausible level of overall rise would be 4 feet by 2100, with a range of up to 6.5 feet as a potential sea level rise. The 2015 estimate put the average height at 3 feet with the maximum at 10. Okay? So this is simply just how fast the information changes, because as the ice at the moment picks up speed and melt, all the numbers get changed. They get changed fairly quickly. Okay? So what was happening with the glaciers so far is we've seen the fracturing on the surface area. We've seen the formation of moulins, these holes that basically the meltwater runs all the way down through the glacier, gets down to the bedrock, helps lubricate the movement of the glacier, so the glacier speeds up as it travels, and so it calves that much faster and transfers that much more ice into the water as a form of sea level rise. Okay? Now, those numbers were wild enough, but now what we're really looking at is how much warmer the West Antarctic has gotten in the last few years. And in 2016, just last year, the feeling was that the estimate was whatever number you wanted to use in this column, add 5 feet to it. They were looking at about 5 feet of added sea level rise because of losing large glaciers in the West Antarctic ice sheet, probably by the year 2100. Okay? And that's why I say the number is dynamic. It's going to be constantly changing as we go out and measure year after year what's really going on. Okay? And these are the glaciers we're talking about in the West Antarctic, the Pine Island and Wales. These are the 2 glaciers that are causing most of the concern right now. These are the other 4. These 6 at the moment are all considered to be irreversible. That is to say, they are going to melt and there isn't anything we can do about it. Now, how fast they melt, that's a whole other question. But those are things that are going to be melting. Okay? And part of what's going on now in the Antarctic and also up around Greenland is we have melting on the top of the glacier from sunlight. We have melting on the underside of the glaciers because now that we've raised sea level, water can now come in and start to erode the glacier. So that makes it melt faster. And the combination of melt here and melt down here causes the whole glacier structurally to become unsound. And so it starts to physically break up internally at an even faster rate. Okay? So, so in all likelihood, sea level is going to change faster than our comfort level. We can't tell you how fast because humans have never seen anything like this before. Okay? The